Hi, today we're going to begin our journey with electron dot structures, also called Lewis structures. And this really is just a beginning. I know this is going to be a long video, but there is actually quite a bit more to learn after this. So what are electron dot structures? Basically, they are a simple graphical representation that help us understand how valence electrons get distributed throughout a molecule. So whether they're shared or whether they're not shared, as atoms form covalent bonds with each other. So you need to know how many valence electrons each atom in the molecule has. And there are two ways you can do that. The first is to look at the electron configuration. In this case, we're going to identify which orbitals have the highest principal quantum number. For bromine, that's 4. You could also write the shorthand electron configuration, which makes it a little easier to see. But we have 2 in the 4s and 5 in the 4p, so that gives us 7 valence electrons. The other way you can figure out valence electrons is by looking at the periodic table. Again, this is tied into what we talked about with the periodic table and electron configurations. I'll try and drop that link down below. And so basically, if you're in group 1, you're going to have 1 valence electron. If you're in group 2, you're going to have 2 valence electrons. If you're in group 3, you're going to have 3, 4, 5, 6, 7, and 8. Now, of course, we've skipped over everything in the transition metals, as well as everything down in the lanthanide and actinide series, the F block. All of those are going to also have 2 valence electrons. For each atom in an electron dot structure, the nucleus is represented by its element symbol. And again, we're starting with bromine, so we write Br. The next thing we do is we add 1 dot around the nucleus for each of the valence electron. Now remember, we figured out that bromine had 7 valence electrons, so let's add those now. Here we have 2, 4, 6, and 7. Now you'll notice that I have these in pairs, and there's a reason for that, because basically what we're looking for, first of all, is 8 electrons around each atom. That would give us the noble gas configuration. So that would be 4 sets of 2, which, since you can think about the element symbol as kind of a square, that gives you 2 dots on each side. The other thing is that electrons are always paired in orbitals when you have a full orbital. So that's the other reason that we write them in pairs. So you can see that bromine does not have 8, it has 7, so it's missing 1 electron. And if you have 2 bromines that each need 1 electron, the way you can solve that is by forming a covalent bond. So you're basically going to share these 2 unpaired electrons. And so there's 2 ways you can indicate a shared pair of electrons. One is like this, so you're basically just putting those pairs in between the 2 nuclei. The other way is like this, by drawing a line to indicate that those 2 nuclei are linked by shared electrons. Most of the time we tend to use this bottom one to signify that there are shared electrons. So how do you draw electron dot structures? This is a multi-step process. I have broken this down into 2 basic phases with multiple steps. In the first phase, we're going to do math. So we're going to start with the total number of electrons that are available in the valence shells of all your atoms. You always do that. And then if you know that all your atoms will obey the octet rule, and everything in this video will obey the octet rule, we're going to do more math. That will help us figure out how many bonds to draw. The results of that math will help us draw the structure. So let's talk about the math phase first. As I said before, the first thing you're going to do is you're going to find the total number of valence electrons in the molecule. So what you're going to do is you're going to go through atom by atom, and for each atom, figure out how many valence electrons that atom has, and then you're going to add up the numbers for everything in the molecule. If you have an ion, that changes the number of electrons you're going to have. So if you have a negative ion, it's negative because you have more electrons than you technically ought to have. So you're going to add the number of electrons equal to whatever your negative charge is. So 1 electron if it's a -1 ion, 2 electrons if it's a -2, and so on. If it's a positive ion, you're going to take electrons off that equal the positive charge. So if it's a +1 ion, you're going to subtract 1 electron from the total. If it's a +2, you're going to subtract 2, and so on. So I'm going to summarize all of this first step this way, and that's a very brief summary for something with a lot of nuance. But hopefully with enough practice, you'll get used to this. The second thing you need to do is determine how many electrons that are necessary for every atom to feel like a noble gas. Now, for most atoms, this number is going to be 8 because of our octet rule. The exception is going to be hydrogen. And the reason hydrogen is the exception is because it only has an electron in the 1s, and for the 1s to be full, you only need 2 electrons. So for hydrogen, it needs 2 to get to noble gas configuration. Everything else needs 8. Are there exceptions to this? Yes. We are not going to talk about any exceptions to anything in this video. That will be another video altogether. So the second step is determine the number of electrons to complete the valence shells. The third step is to determine the number of shared electrons. And the number of electrons that are going to be shared is the number you figured out they needed to reach noble gas configurations in step 2, minus the total number of valence electrons available to be used, which you calculated in step 1. That is just a simple subtraction. Again, this math only works if everything follows the octet rule, because if that's not the case, then the number you calculated in step 2 does not work. Finally, you're going to determine the number of bonds that you need to draw. And basically what you're going to do is you're going to divide the number of shared electrons you got in step 3 by 2. And we're going to abbreviate this that way. So this concludes our math phase. Once we've calculated number 4, we're going to move on to the drawing phase. And the first step in the drawing phase is going to have you write the symbols for each of the atoms in your molecule and then add bonds between the atoms. Now, some people are like, what do I connect where? A lot of times if you have a complex molecule, they're going to write the atoms in the order that they're connected in.
If you have a small molecule
with only one central atom, so you have one atom in the middle and a whole bunch of things coming off, that atom is usually written first. And then somehow you need to distribute the number of bonds you calculated in step number 4 between these atoms to hold them all together. Sometimes it's going to be obvious how you do that, and other times it's not. And you'll see examples of both in this video. So all of those steps we're going to summarize this way. Write symbols for atoms and put in bonds. Step 6 tells you to take the rest of the electrons, the ones that haven't been used for bonding, and distribute them amongst the atoms so each has a noble gas configuration. I wrote so each atom has an octet, but that is not appropriate if you have hydrogen. So just head for a noble gas configuration. So if you need to think about how many unshared electrons you have, you're basically going to subtract the number of shared electrons that you got in step 3 from the total number of electrons you had in step 1. So that's what step 6 is about. And then finally, this only is true if you're drawing a polyatomic ion. We're going to place square brackets around the structure and indicate the charge as a superscript. So that's what step 7 is about. Okay, so that is pretty complicated, and it actually makes a lot more sense if you apply these rules to a specific problem. So let's go do that right now. So we're going to start with something easy. We're going to start with nitrogen gas. So let's start with a math phase. Molecular nitrogen gas has 2 nitrogens in it. The first nitrogen has 5 valence electrons. The second nitrogen also has 5 valence electrons. That gives us a total of 10 valence electrons. So we're going to pop that number up here and keep that part there. I'm going to erase the math as we go along, but I'll keep the answers over here by each step. The second thing we need to figure out is how many electrons would be needed for everything to have a noble gas configuration. So the first nitrogen would need 8, and the second nitrogen would also need 8, so that's 16. So we're going to pop that over by step 2, and now we're going to determine the number of shared electrons. And remember, this is going to be step 2 minus step 1. So we have 16 minus 10. That gives us 6 shared electrons. And now we're going to determine the number of bonds. And that's just going to be 6 divided by 2. We always divide by 2, and that gives us 3 bonds. So now we've finished the math stage, and we can actually move on to drawing a structure for nitrogen gas. So we're going to write symbols for atoms and put in the bonds. So let's start by putting our nitrogens in, and then we're going to put in our bonds. We have 3 bonds, and there's really only one place to put all 3 of these bonds because we only have 2 atoms. So we have to connect these 2 atoms. So we're going to go 1, 2, 3. 3 bonds. And now let's distribute the unshared electrons. So we started with 10 electrons, we've used 6, that gives us 4. Where are those going to go? Well, if you look at this nitrogen right here, it has 6 shared electrons, but it still is not to 8 yet. It needs 2 more to get to 8, so we're going to put 2 electrons right there. And then the other nitrogen also needs 2 more electrons, so we'll put the other 2 electrons right there. And at this point, I like to go through and just count electrons to make sure that I have used up all the total electrons and I don't have too many electrons. So 2, 4, 6, 8, 10. The last step says if ion add brackets to charge. That's not applicable because this is not an ion. So let's try something that is an ion just to see how that works. We're going to do the hypochlorite ion, OCl-. So let's find the total number of valence electrons. Oxygen has 6 valence electrons. Chlorine has 7 valence electrons. And then because we have a negatively charged ion, we have to add electrons for the negative charge. Now we have a -1 charge here, so we're going to add 1 electron. And if you add those all up, you get 14. That is the total number of valence electrons. So now that we've calculated that, let's determine how many electrons we need to complete the valence shells. Oxygen is going to need 8. Chlorine is going to need 8. That gives us 16. So that is the answer to number 2. Now the number of shared electrons is going to be number 2 minus number 1, so that's 16 minus 14, which is 2. And then the number of bonds will be 2 divided by 2, and that will be 1. So we're going to have 1 bond. Now we can draw it. We're going to write the symbols for the atoms, oxygen and chlorine, and we're going to put in our bonds. We only have 1 bond, and there's only one place for it to go. It's got to go between the 2 atoms. And then we need to distribute the unshared electrons. How many unshared electrons do we have? Well, we started with 14, and we have only used 2 so far, so we still have 12 left. If we look at the oxygen, it only has 2 electrons. It needs 6 more to reach 8, so 2, 4, 6. And then chlorine also needs 6 more to reach 8, and so 2, 4, 6. So we've added 12, and I'm going to just go through and double check that we have 2, 4, 6, 8, 10, 12, 14 total electrons used, which is how many we started with. The last step says if ion add brackets and charge. So we're going to put square brackets around it like this, and we're going to add a negative sign for our -1 charge. Now we're going to do a more complex molecule, and this is more complex because it has 6 atoms instead of the 2 that we've done so far. So let's go ahead and do our math. We have 2 carbons, and instead of writing carbon has 4 and the other carbon has 4, I'm just going to write 2 times 4 because each of them has 4. So that gives us a total of 8. We have 4 hydrogens, each has 1, so that's going to give us a total of 4. And so we have a total of 12 valence electrons. Now we need to determine how many electrons we need to get everything to noble gas configuration. Here we have 2 carbons. Each of the carbons needs 8, so that means 16. We have 4 hydrogens. Each of the hydrogens needs 2, so that's 8. So that gives us a total of 24 electrons for number 2. Now that we have done that math, we can easily determine the shared electrons. We have 24 minus 12, so we have 12 shared electrons. And then that tells us that our number of bonds is going to be 12 divided by 2, or 6. Now we get to write symbols for atoms and put in the bonds. So there are a number of ways you could do this, and sometimes you have to do it by trial and error. So I could put in a carbon, and I could say, well, let's see, how about 3 hydrogens, and then a carbon and a hydrogen? How about that? And then you start putting things in, and you're like, okay, 1, 2, 3, 4, 5, because you always start with 1 bond between each atom and the atom next to it. And then you're like, oh, I need another bond. Where is it going to go? Well, if you put it between carbon and hydrogen, right here, hydrogen's going to have 4 electrons, which is more than it can have, so we can't do that. It's going to have to be between the 2 carbons, like this. If you look at this structure, and you look at this particular carbon right here, you can see that it has 2, 4, 6, 8, 10 shared electrons, which is more than it can have in its valence shell. So this structure just doesn't work. So let's just toss that away and let's try something else. I'm going to put carbon here, and I'm going to put 2 hydrogens on that carbon. I'm going to put carbon here and 2 hydrogens on that carbon. And now I'm going to put in my bonds. That's 5 so far, and we need that 6th bond. So I'm going to put it between the carbons again. Hydrogens, you'll discover, really can only take 1 bond. So that's the only place you can put it. Distribute unshared electrons. Well, we started with 12 electrons and all 12 were shared. So we have no unshared electrons. This is it. This is our structure. It's not an ion either, so we don't need to do step 7. Here is yet another ion, the nitrite ion, NO2-. Let's do our math. Find the total number of valence electrons. We have 1 nitrogen, which has 5. We have 2 oxygens, which have 6 each, so that's going to be 12 electrons. And then we also have a negative charge, so that's going to be 1 extra electron. So you add those all up, and we have 18 valence electrons. Now let's figure out how many electrons we need to get everything to noble gas configuration. Nitrogen needs 8. Each oxygen needs 8, but there's 2 oxygens, so that's 2 times 8, or 16, and that means we need 24. So how many shared electrons do we have? It's just 24 minus 18, which is 6. And that gives us 3 bonds. So let's move on to the draw stage. Let's write symbols for our atoms and put in the bonds. Here's an oxygen, a nitrogen, and an oxygen. 1 bond, 2 bonds. So now everything's connected, but we still have 1 bond to go. So one of these must be a double bond. Now, some people say, how do you know that this doesn't look like oxygen, oxygen, nitrogen? So let's try that as well. And let's see how it works. So we're going to distribute the unshared electrons. We have shared 6 electrons. We started with 18. There are 12 electrons. And if you look at this, this oxygen has 4 shared electrons, so it needs 4 unshared electrons. The other oxygen has 2 shared electrons, so it's going to need 6 electrons. And then we're going to have 2 here. As far as the middle one goes, this oxygen again is going to need 4, and this is going to need 6, and this is going to need 2. So we have 2 possible ions. And remember, they are ions, so both of these, let's write brackets and negative charge. How do you decide between these 2 things? Well, how do you know what goes in the middle? There are 2 ways you can tell. First of all, if the molecule has 1 central atom, it's almost always written first. But if you think back to our naming scheme, which element do we write first? We write the least electronegative atom. Now, sometimes the least electronegative atom is hydrogen. Hydrogen can only form 1 bond, which is not a good thing for a central atom that needs to form multiple bonds. The central atom is always going to be the least electronegative atom that isn't hydrogen. And the reason that is because the more electronegative atoms are going to pull electrons towards them. The central atom needs to share electrons. And if it is very electronegative, it does not share well. It wants to keep all the electrons for itself. So you're always going to look at the least electronegative element, which in this particular case is going to be nitrogen, 3.04. So this is the structure that we're looking for. Now we're going to do an electron dot structure for acetaldehyde, C2H4O. You'll also see it written CH COH, and I prefer that when I'm teaching people electron dot structures because it shows us how we write formulas in a way that indicates structure. So let's go through and do our math because we always have to get that out of the way first. Our total number of valence electrons, we have 2 carbons. Each of those is going to have 4 valence electrons. We have 4 hydrogens, each with 1 valence electron, and then we have an oxygen with 6. So if you add those up, we have 18 valence electrons. How many electrons do we need to get to noble gas configuration? Well, each of our carbons will need 8, so that's 16. Each of our hydrogens will need 2, so that's 8. And then our oxygen will also need 8. So that gives us 32. So the number of shared electrons we have is going to be 32 minus 18, which is 14. And that tells us that we're going to have half of 14, 7 bonds in our molecule. Let's write the symbols for the atoms and put in the bonds. So we're going to put the C, and the second structure, this one over here, tells us that 3 of the H's go around that C. The next thing we're going to encounter is a C bonded to an O and an H. We have 7 bonds, 1, 2, 3, 4, 5, 6, and we need a 7th bond. And so one of the things you can do is you can look and say which atom still has room for another bond. If you look at this carbon right here, it has 4 bonds already. It has 8 shared electrons. It cannot take any more bonds. How about this carbon? It has 6 shared electrons, so it does have room for 2 more shared electrons. What else will share those electrons with a carbon? Well, it can't be hydrogen because hydrogen can only have 1 bond, and so it's going to be oxygen. There's our second bond. Now we get to distribute our unshared electrons. We started with 18 electrons. We used 14 of them so far, so we have 4 left. So we're going to put them around the oxygen, which is the only thing that does not yet have 8 electrons. So we're going to put them here. And this is not an ion, so that's where it stops. So we are using electron dot structures to help us see how electrons get shared within a molecule. If there's a double bond, where does that double bond go? What 2 atoms does it connect? Is there a double bond at all, or is it all single bonds? All of these things we can figure out by doing an electron dot structure for a molecule. So this is something that you will use in pretty much all advanced chemistry that you see from here on out. And so we're going to give this a lot of practice in class. I hope this was helpful, and I look forward to seeing you again soon.